Thank you. So the paper appeared yesterday, and this is work done by my PhD student, now postdoc, Mohammed Madi Derekshani, master student who was interested in doing a project, Diraj Varghese, our proud collaborators from Cohere Labs, Marci Fadaye, and myself. Yes. Yeah, so this is the problem we are addressing. So we are living basically in a monolingual AI world with all of us, dominated by the English language. And for a specific type of AI, the one I will be talking about today, so how to convert a text prompt to a picture or an image. This is very much English-centric, so always prompts are always in English and to generate all kinds of beautiful pictures. However, by focusing on English, you only serve about 5% of the world's native speakers. So 95% of our population on this planet is left out. Well, this creates a significant barrier to global access and really perpetuates digital inequity. And this is not limited to the global south. Europe is probably the best example with all the languages and cultures we have within our union. So we want to address this problem. So text to image generation is a fast-paced field. Things are moving very quickly. So here you see a scatter plot of methods in terms of their gen eval performance. So that is a specific benchmark, actually by people from Leon. And on the x-axis, you see the number of billion parameters of these models. So to give you some example, Shouo was a nice paper from the National University of Singapore that appeared at iClear a few months back. It was online somewhere in November, I think. Janus Pro is from the people from DeepSeek. It appeared in January of this year. And only a month ago, Blip 3.0 was released. This is by people from Salesforce. And you can also see that almost all these models are English only. Some of them, like Blip 3.0, rely on a multilingual LLM as part of their multimodal tactic. But they are not natively multilingual in the sense that there is no real connection between the text, the language, and the image representation. So they are separated. And also again, echoing Genia, there is very limited openness among approaches in this area. So some people release weights, but very often code is not available and data is unavailable. So I'm going to present our model, NeoBabel. This one is natively multilingual. It is efficient and open. So we are state-of-the-art, or we match state-of-the-art for the English language, while being twice or 4 times as efficient as alternatives. We are fully open, so everything we have done will be released in the next few days. And we have, from the get-go, native support for 6 languages. Because all benchmarks are English only, we also created multilingual variants of existing benchmarks. And when we compare on those multilingual benchmarks, we see a big gap between the best alternative approach of Blip 3.0. And we provide models for English, Chinese, Dutch, French, Hindi, and Persian. So quite a diversity of languages. All right, so what do we contribute here? We believe this is the first natively multilingual text-to-image generation framework. It comes with a large-scale multilingual image dataset, a unified multimodal architecture with staged training, new type of benchmark built on existing benchmarks, and also new metrics to take into account the abilities that come with being multilingual. And we release everything as an open toolkit for inclusive and open research. All right, so I'm going to talk about the different contributions and what we did to get to our model. So let's start with data, the thing that is so crucial and nobody wants to work on. There is already a lot. So here are a bunch of data sets that are available, but they are all focused on the English language. So of course we have ImageNet, but we also have closed captions, the SAM dataset, Lion Aesthetic, JourneyDB with synthetic images, and an instruction tuning dataset provided by the authors from Blip Trio. So this is a total of 39 million image and caption pairs, but all focused on English. So what did we do? We expanded these existing datasets by using model-generated recaptioning. So we didn't do this all manually ourselves. We used state-of-the-art foundation models to help us, so to say, and also for the translation of labels and captions. I will give you some examples for various datasets. So this is the well-known ImageNet dataset. So we used a experimental model from Gemini to translate the labels into the 6 languages we are working with. So here you see some random samples with their 6 translations. We also recaptioned several of the captions in the dataset. So here you see an example from the conceptual caption dataset. So we did this recaptioning with an intern VL model proposed at CVPR last year. And first you see the original caption and then the one that is recaptioned based on this model. Now, of course, there is still some validation to be done. So we check for length filtering, language validation, whether there is a mismatch between the visual and the text, and also whether there are sort of not suited for work elements in the recaptioning. Here's an image from JourneyDB. This is synthetic data, and here you again see the original caption and the recaptioned variant of it. So notice that it is much more fine-grained detail. So this is helpful because the more specific the language, the more specific the image you can generate as well. And here we did recaptioning and translation. So we first recaptioned, and then in the second stage, we translated all these dense captions to the international variants. And here we used the NLBB model by people from Meta AI, UC Berkeley, and Johns Hopkins University. And last but not least, we used also Blip Trio instruction tuning data. So this is a high resolution, high quality data that is synthetic and also helps for getting sort of like a good variety in the data set. And what we did here, we took the existing English caption and we translated again with this NLBB, NLLB. Okay, so after this exercise, so for the ImageNet, we translated it, so it's a factor 6. Others were not translated, but only recaptioned, and so on. So for a total of 124 million image caption label pairs. So now we have sort of like a truly multilingual data set from which we can use to train our foundation layer. All right, so let's go a little bit deeper into the training. I have a one-slide summary of the architecture. So this is a multimodal architecture, but it uses an interleaved setup of text tokens and image tokens. So there is no encoder involved here. So what we do is we first tokenize the text, and for this we use the Gemma2 tokenizer. Then for the image tokens, we use the MacVid V2 quantizer. This was also used by the Showo paper I mentioned earlier. And these tokens are then interleaved, concatenated into one representation together with special tokens to indicate the transition from text to image, and also very important, we do masking. So the masking is only done on the image patches. So although we have a text and image representation, we will only mask the image tokens. The NeoBabel architecture itself is basically the Gemma2 LLM decoder-only transformer, and which we changed a little bit by adding about 8,000 new learnable embeddings for the visual tokens. Now, how is this beast trained? It only uses a diffusion loss that tries to sort of like, given a masked patch, tries to reconstruct the masked patch given the original pixel, so to say. So the text tokens are in there, but are not really optimized as part of the loss that is purely focusing on the image patches. Now, we have a hybrid attention approach. So the text tokens follow sort of like the standard causal relation, and for the image attention, we use a bidirectional diffusion attention. Now, with inference, what you do is, given the prompt, you start with a completely masked image, and the NeoBabel architecture will then slowly sort of like to fill in the patches and reconstruct the image given the text prompt. So that's an important element of the approach. And the second important element is the training stages that we use. So this is very specialized training procedure that has multiple stages. So first, we start with what we call progressive pre-training. And in stage 1, we want to learn the basic relationships between pixels and simple text captions. So here for this stage, we use the ImageNet 1K dataset together with our multilingual extension indicated by the small m. Then in stage 2, we scale up. So this is a combination of 3 datasets. So we have a total of 94 million image and caption pairs. And we continue the pre-training. And then at the end of this pre-training, there's a third stage where we do the refinement. And here we use Leon aesthetic and also the synthetic data from the Midjourney DB. This is all done on 256 by 256 resolution. After this stage, we go into progressive instruction tuning at a slightly higher resolution. And we also now use more specific datasets, so Leon aesthetic, Midjourney DB, and Blip 3.0. And we use different mixtures during fine-tuning. So for the first stage of instruction tuning, we use a mixture that emphasizes more the Leon aesthetic dataset in favor of the other two. And in the final tuning stage, we emphasize more on the Blip 3.0 dataset. All right, so this is what we did in terms of training. Then comes evaluation, but I first need to explain what we did. So we introduced a comprehensive multilingual evaluation suite that contains multilingual extensions of 2 commonly used benchmarks for this domain, being GenEval and DPG. And we extended this to the 6 languages we have, together with some new metrics, but I will not go into deeper detail of those in this talk. They are in the paper. So this is how GenEval works. It has basically defined 6 object-focused tasks that allow to evaluate the compositional image properties of a generated image given a prompt. So for each of the 6 tasks, they have defined about 100 prompts each together with their paired with color and object properties. And because they are paired, they can run sort of like an off-the-shelf object detector. I believe it's a mask-to-former that they use, that then analyzes the generated image to verify whether indeed, given the prompt here, a photo of a purple backpack and a white umbrella, whether the backpack and the umbrella are indeed in there and whether the color attributes match. If this matches, your score goes up, and then you can compute your final score, so to say. So this is the usual approach. Now, it's very simple to make this suitable for our evaluation. We just add multilingual variants of the prompts, and we can use the rest of the GenEval setup as is. The final score is now only computed per language, so we have multiple scores. So what does this look like? So here we plot it for 3 languages, and we compare Showo, Blip3O variants and Janus Pro 7b with NeoBabel approach. And what we see, these are non-English languages. So for French, Blip3O can still do a reasonable job. But when we go to very much more specific languages like Hindi and Persian, they really collapse. And this is not surprising because Showo uses as its underlying language model Phi 1.5, which is English only. So it has never seen any other languages, so it cannot do this. Janus Pro is based on a DeepSeek LLM, which apparently is also not very good in international languages. Blip3O is best. It uses a multilingual LLM under the hood, so that is the most advanced one, but it doesn't have the connection between the language and the image tokens. So it's underperformed compared to our NeoBabel. There are not too many people speaking Dutch in the room, but I'm showing some results that compares Blip3O with NeoBabel. So what you can see here that both do a good job, but there are interesting nuances. So the second one says create a photo of a dinner table together with a bear. But in a bear in Dutch is beer, and yeah, so it makes a glass of beer out of it because it has this strong prior on English. While for NeoBabel, it connects the words really to the image, so it does a better job. Similar. Sorry? Similar. The last one now is not completely similar, so it is asking for a purple glass of wine and a black apple. So the nuances is really in the time, so it misses the glass of wine sort of there. And there's also some hallucination with the sofa on the top. Okay, we do one more evaluation. This is dense prompt generation benchmark, also known as DPG. It has a slightly different setup. It is suited for longer prompts. So what they do is, how they evaluate is also quite nice. Given a prompt and a text-to-image model, let it generate 4 different images. Put them in a grid and then let them be evaluated with a visual question answering model based on paired questions that come with the prompt. And here they use mplug large as the VTA model. The output is then verified, and so you can sort of like score your model. Again, the multilingual extension is easy. Just create 6 different languages and then you're up and running. So let's also have a look at those results. So again, what we see here that for English, we are not the best, but comparative. So here Janus Pro does a really good job, but it needs much more parameters. But as soon as we go to any of the other languages, the NeoBabel approach is much more effective. Then one ablation to demonstrate the effect of the different training stages that I talked about. So the 3 stages in pre-training and the 2 in instruction tuning. So we see different effects depending on the benchmark. But in all, so what we can conclude is that this multilingual image data, the quality thereof and resolution enable fine-grained improvements. So that is really depicted in the left plot for Gen eval. So really after the instruction tuning, results get a very good boost because that is very specific, high-level quality data. And for the other benchmark, it really helps for generalization to have all the stages after one another, and it's quite interesting to see the jump from stage 1 to stage 5 in all cases. So there's really it's quite effective. Briefly, some new applications that we enable because of this new multilingual visual connection. So we can do things like multilingual in painting. So given an input image and a mask, you can instruct it to do all kinds of things with the masked area, no matter the language. And this one I find more interesting. So now you can sort of like collaborate together internationally on the canvas, and everybody can sort of use their own language, mix it up in a multilingual prompt and generate the results. So in the first one, we combine English, a close-up photograph of a corgi dog. Then we switch to Dutch. De hond draagt een zwarte hoed en een ronde donkere zonnebril. And finally, we do some French. Le corgi a une expression joyeuse avec la bouche ouverte et la langue tirée, donnant une impression de bonheur ou d'excitation. And it will generate the image we have over there. So this is a new way of collaborating with multiple people across different languages.
Good for your vision.
Yes. And then last but not least, because open is an important driver in the ELLIOT program, we make everything available. So the website is already in there, but Mohammed is working hard with Diraj to make the rest of the data available very soon as well. So codes, checkpoints, all the data, the benchmark extensions, everything. Okay, final words. So multilingualism here is a catalyst and not a trade-off to which you lose performance. It actually enhances performance, so it is a worthwhile thing to do. We are a performant text-to-image generation model while being smaller and much more inclusive than existing work. We provide a curated dataset, an architecture, progressive training strategy, and a rigorous evaluation framework. This is all fully openly available to democratize research and expand, hopefully, the languages to even more languages to become even more inclusive. And with this encouragement, I would like to thank you for your attention and leave it here.